Hello everyone. Today what we're going to do is we're going to take a look at how we use Punnett squares to solve some genetics problems that are not quite as clear-cut as the ones we have been doing. In all genetics problems involving Punnett squares, there are 5 things that need to be documented. This becomes even more important when the problem is less clear-cut. You want to be able to show other people exactly what you were thinking. As I model how to do these problems, you will notice that I think through each of the 5 parts as we go. When we worked on our simple monohybrid crosses, we got a considerable amount of information. We were told what was dominant and what was recessive, and we were also told the genotypes of the parents. In this case, some or all of this information will be missing. So let's start. In turtle doves, low cooing big L is dominant over high cooing. 2 turtle doves, 1 a low cooer and 1 a high cooer, produce 9 low cooers and 10 high cooers. What were the probable genotypes of the parents? It may seem like there's not enough information, but there actually is enough information to get us part of the way through the problem. Very clearly, we can see what the dominant and recessive are, so we can fill out our key. A big A is going to be low cooing, and a little a is going to be high cooing. So we move on to our parental genotypes. Now, they have told us that one of the parents is a low cooer. Now, that means that there is a big A for that parent, but we're not quite sure if it's a homozygous dominant or a heterozygous. So we're going to leave a little blank there where that second letter would be because we don't know what it is. We know that the second parent is a high cooer. Now, high cooing is a recessive trait, which means that this parent has to be a homozygous recessive. So we actually have more information than we think. The next thing that we're going to do is we're going to fill out our Punnett square with as much information as we have. So we know that we have a big A, but we also know we have a blank. So we're going to leave that blank in our Punnett square. We have a homozygous recessive parent, so that's going to fill out that whole top part for each of the columns. The next thing that we're going to do is we're going to fill out the Punnett square as far as we can, putting that blank in place for the one that we don't know. So now we need to use that last piece of information given to us in the problem. We see that our offspring end up having 10 low cooers and 10 high cooers. Now, these are actual numbers, and although when we use our Punnett square, we get like 50-50 or 75-25, in real life, it doesn't work out quite that clean. But we can see that we have 9 low cooers and 9 high cooers. So that's a total of 19. So I've got 9 out of 19 low cooers and 10 out of 19 high cooers. Now that is about a half and half. And I can see my high cooers, these guys right here, those are my big A, little a. I also, however, have to get these low cooers. The only way that that is going to happen is if this low part of our Punnett square ends up being homozygous recessive. So that would mean that this parent right here would be a big A, little a. So I can go ahead and fill that in. Now, this also means that I can round out my problem by filling out the remainder of the Punnett square as it would look based on the probabilities. So this is going to be 2 out of 4 big A, little a, 2 out of 4 little a, little a. And my phenotypic ratios based on that are a 2 out of 4 high cooer and a 2 out of 4 low cooer. And although this is not exactly like the actual numbers in the problem, they are close enough to justify that this is the parental genotype. So here's a second practice problem. Now, if you would like to try this before I go through the problem, pause the video now, fill it out, and then follow me as I go through the example. In tropical fish, iridescent or shiny scales are recessive and make the fish more valuable. A clutch of eggs from a pair of tropical fish were hatched, and 17 out of the 75 baby fish had iridescent scales. What were the probable genotypes and phenotypes of the parent fish? Unlike the last problem, we don't have any information about either of the parents. All we have is the information about the offspring. We do have enough information to fill out the key. We know that iridescent scales are recessive. That means that not having iridescent scales is dominant. Now, the next thing I would normally do would be the parents. However, we don't have enough information for that. So I'm going to move on to my Punnett square. I have nothing to put on the outside of the Punnett square, but I do have something to put on the inside of the Punnett square. I know that 17 out of the 75 baby fish have iridescent scales. Now, if I do the math on this, 17 out of 75 is about 25%. 25% have iridescent scales, which would be a homozygous recessive trait. So if I'm thinking about all of the Punnett squares that I've done as practice, I know 25% is one little corner of the square as a little a. Now I'm going to start working backwards. In order to get that combination in that corner, that means a little a has to be here and a little a has to be here. Continuing to follow Punnett square patterns, I would have a little a here and a little a here. Now, if 17 out of 75 have iridescent scales, that means that the rest of them are going to have non-iridescent scales. So I am going to need for each one of these boxes to have a big A in them, which means that there would be a big A here and there would be a big A here. That means that a big A would also go in this box. Now, having done this, I'm going to figure out my genotypic ratios. 1 out of 4 would be big A, big A. 2 out of 4 would be big A, little a. 1 out of 4 would be little a, little a. Now, I can't see that in the problem, but I can see that 3/4 will have non-iridescent, and I'm going to abbreviate here, and 1 out of 4 is going to have iridescent, and that is consistent with what we see in the problem. So the very last thing I'm going to do are my genotypes and phenotypes of the parent fish. So a big A, little a for one parent, heterozygous, and a heterozygous genotype for the second. This means that both parents are non-iridescent. So I have solved the problem that was asked, which is what are the probable genotypes and phenotypes of the parent fish. All right, so we have one last practice problem. The ability to smell asparagus in your urine is recessive. Even though the father has the ability, none of his 12 children have the recessive trait. What is the likely genotype and phenotype of the man and his wife? So the first thing that we're going to do is make our key. This is a long description of a trait, so I'm going to abbreviate it as dominant is a non-smeller and recessive is a smeller. Now, in this case, we have a little information about the father. We know that the father has the ability to smell asparagus, and since this is recessive, that means the father is a little a parent. Now, all we need to do is find the mother's genotype. We're going to use blanks to represent her, and we're going to go ahead and we're going to fill out the Punnett square as far as we can without her information. So from Dad, we know that every single one of his children is going to get a recessive version of the trait. Now we're going to take a look at the information given to us about his children. We know that none of them have the recessive trait. This means that every offspring has a big A in their genotype. Now, as we look at the square so far, we can see that every single one of the squares has a little a. If another little a was right next to that, then we would have offspring that would have that recessive trait, but we do not. So in order to get every offspring with a dominant phenotype, that means every box has to have a big A in it. That means that mom's genotype has to be big A, big A. She needs to be a homozygous dominant. So that would mean that every single one of the offspring, 4 out of 4 of them, would be a heterozygous genotype. It also means that 4 out of 4 of the offspring will be non-smellers, and that is consistent with what we see in the problem. Now, the only other thing that we need to do to complete this problem, since we have the genotypes of our parents, is to write their phenotype. We know that dad is a smeller, and we know that mom must be a non-smeller. So that is 3 different practice problems. If you go to the attachment that was on this video, you should have a number of practice problems to help you to understand and become accustomed to following the patterns of the genetics. So good luck with that. Check the key when you're done.